Hello everyone, my name is Shenkang Lin. I'll be presenting our work called Art, Abstraction Refinement-Guided Training for Provably Correct Neural Networks. This work is done by me and my colleague He Zhu and my advisors Rupsha Samantha and Suresh Jagannathan. Let's get started. Neural networks have proven its power in various applications, especially in the last decade. From identifying a cute puppy image to comprehending long paragraphs in a newspaper to making decisions in an autonomous vehicle, neural networks have shown great applicability in many scenarios. However, neural networks are like black boxes. They may come with many intriguing behaviors on all corner cases, such as the well-known local robustness property. Suppose you have an image of a panda. Now, if you add some small noise to the image, which is not recognizable by human eyes, but now the classifier may recognize that as a totally different species, like a gibbon. Although in the human eye, everything still remains the same panda. This kind of unexpected behaviors is especially troubling in safety-critical scenarios. For example, in an unmanned craft controller. In this talk, we are particularly interested in this kind of safety properties formulated in the form of the input and output constraints. Phi in implies phi out. Specifically, we want to ensure that the unmanned craft controller does make certain actions to avoid the craft from crashing onto the ground, just like the bottom right GIF is showing there. The research question we are interested in this paper and in this talk is that, can we enforce a neural network to satisfy general safety property phi in a correct by construction way? By saying correct by construction, we do not want the post-facto verification methods for neural networks. Otherwise, if you realize that the network you have is unsafe, you still need to feed it back to some training procedure, and there is no guarantee here. After all, we want to bake in this notion of safety property in the training procedure itself, and get the guarantee such that as long as the training terminates, the network presented to us has this safety guarantee. We begin by defining an illustrative example which embeds the problem setup and the key idea of the art approach for correct by construction training. Suppose there is a simple alert system used in some autonomous vehicle. The job of this alert system is to report to the central controller whichever vehicle it finds dangerous suspiciously. To do that, a simple two hidden layer ReLU network is being applied. It takes as input a feature vector of size 2, where the first one is the variable v representing the relative speed of the other vehicle comparing to the own vehicle. The second is the variable theta, which represents the relative direction of the other vehicle to the current vehicle. The network applies ReLU activation functions. After propagating the values, eventually there are two output values, which correspond to the prediction scores for two categories. The first one is to report this vehicle, and the second one is to ignore it. The neural network controller chooses whichever category is larger and use that as the advised action. Now, we can formulate the kind of safety properties we are interested in. For example, we measure that the objects in front of the vehicle that are static or moving closer to us should always be reported. We can ascribe ranges to represent these terms. For example, we may assert that for all theta within the range of 0.5 to 2.5, which represents that it is in front of the vehicle, and for all v within the range of 0 to 5, which represents that it is either static or moving closer to us. In these cases, the outputs should always be the case that y1 is greater than or equal to y2. To enforce the safety property on some neural network, the very first question we want to ask is, how do we know if a trained neural network has already satisfied phi, the safety property? A typical approach is to encode both the neural network and the safety property into some external solver, like an SMT solver or a mixed integer linear programming solver. Then the solver may return to you two kinds of results. First is the solver says it's safe. Then you are good to go. The second one is that the solver may tell you, no, it's unsafe. And with that, it presents you several counterexamples, which is the witness of how that safety property is being violated. A straightforward follow-up question is, can we somehow utilize these kind of counterexamples in the training process to enforce the safety property phi? Unfortunately, it does not work well by directly incorporating the counterexamples. The first reason is that the counterexamples are usually very few in the number. Each call to the external solver usually only returns one or two or several counterexamples. Especially comparing to the hundreds of thousands of training samples in the data-driven training approach, this few number of counterexamples does not count that much. The second reason is that the counterexamples may be endless. Consider this diagram, for example. The dark yellow region here is the genuine reachable state of the entire network with respect to some inputs. And the blue point here are the sampled input states. Then, for these many blue points, all of them have happened to reside in one side of the safety property, which is the safe side. Then empirically, this seems fine. But the external solver may tell you that no, there is some other counterexample found here. And even if you consider that take into the consideration, there may be yet another counterexample found returned by the solver. The point I want to make here is that these counterexamples, they are discrete, so there may always be new ones. Essentially, this is like augmenting the current deep learning training workflow with more data points. In that same sense, there is no safe by construction guarantee, just as there is no safe by construction guarantee in the current training workflow. We argue that correct by construction training should be based on some metric that can directly evaluate the entire region, but not on individual points. We will elaborate this more in the next slide. Therefore, it comes the over-approximation-based neural network certification techniques, which are already heavily used in program analysis, numerical analysis, and other fields. Here, we just randomly use a hexagon for illustration purpose. In reality, abstractions like intervals, zonotope, octagon, polygon, and many others are being used. These kind of over-approximation-based certification techniques are often sound but incomplete. They are sound in the sense that as long as the over-approximated abstraction is guaranteed to be safe, then all those genuine reachable states within the abstraction are also guaranteed to be safe as well, just as shown on the rightmost figure here. On the other hand, they are usually incomplete. Take the example here, where the red bar represents another safety constraint. Then empirically, we observe that the genuine reachable states, represented by the dark yellow region here, they are all on one side of the safety constraint, though they are safe. However, the over-approximated hexagon region cannot guarantee that. And in this case, the certification tool cannot give you anything meaningful result. Now, we can proceed to discuss the architecture of ART and see how that achieves safe by construction training guarantees. In a typical training procedure, the training data is fed into the neural network. And then after propagations in the layers, the neural network outputs some concrete outputs. That concrete outputs may be used to compute some loss using some objective functions. The loss is then later back propagated to optimize the neural network parameters. The key part we're adding here is to also encode the neural network in some abstract domain. And we also take the input abstractions from the safety properties, which are the phi in, and use that as the input for the neural network on the abstract domain. Then, after propagating the abstractions layer by layer in the network, there will be over-approximated outputs generated. In the same notion as the loss in the concrete domain, we can also define a loss function on the abstract domain with respect to the safety constraint phi out here. This is the key part, which is to define this loss function for the over-approximated outputs that has this guarantee. The guarantee that as long as this loss is less than or equal to 0, then the phi out, the safety constraint, can be proven to hold. In other words, we have identified a sufficient condition, which is loss less than or equal to 0, and use that as the termination criterion for the entire training procedure. In this way, we also require the loss function to be designed accordingly. Let's come back to our illustrative example, where we use the simplest interval domain to demonstrate the computation of over-approximated outputs. Note that the interval domain here is only used for illustration. In the paper, we did use some more sophisticated abstract domains in the evaluation. In the interval domain, each neuron is now maintaining an interval of lower bound and upper bound, rather than the concrete scalar value as before. The propagation of these intervals through interval arithmetic, and also the ReLU activation functions are specifically handled in the interval domain, where take the node P2 to node Q2, for example. If the interval maintained for P2 has a negative lower bound, the ReLU function on the interval domain will just reset that lower bound to 0. Here in this example, the over-approximated output is computed for the input region of V belonging to the range of 0 to 5 and theta belonging to the range of 0.5 to 2.5, which is exactly the safety property we have defined previously. With that, the over-approximated output ranges for Y1 and Y2 can be computed. Apparently, this computed over-approximate output for Y1 and Y2 cannot indicate that Y1 is always greater than or equal to Y2. Observe that Y1 can take negative values, while Y2 is always positive, according to the computed over-approximated output for Y1 and Y2. So, it should be used, this kind of information should be used in training to optimize the weights. And that's exactly how we want to define our loss function, just to bake in this kind of information to aid the training. Therefore, our correctness loss is defined to be roughly the shortest distance to make all over-approximated output safe. Take the diagram example here. There is a safety constraint, which is represented as the black bar in the middle, which splits the entire state space into two parts, the safe part and the unsafe part. Essentially, our notion of correctness loss is defining how much distance it is to move the entire over-approximated abstraction to the safe side. Here, it is just this red bar, this long, so the loss can be defined to be this much. Coming back to the example, for phi out, to ensure that when the loss is less than or equal to 0, y1 is always greater than or equal to y2 is guaranteed, we can define the loss function to be the first computing the y2 minus y1, and then applying the ReLU function here. Essentially, it conveys the idea that even the largest possible value of y2 is still smaller than any possible value of y1. If this is the case, we can entail that when the loss is less than or equal to 0, phi out always holds. To make it efficient, we do not require strictly being the shortest distance. See the example here, where there is yet another violet bar as another safety constraint. In this case, we do not require the loss to represent the bottom right direction, because empirically we know that the shortest distance to make all over approximated outputs would be to move it to the bottom right direction. And this design choice is for efficiency consideration. In practice, we allow the different combinations of the two or multiple losses. It can be max of them or the summation of them, as long as the requirement loss less than or equal to 0 implies that phi out holds, as long as this requirement is still holds. Moreover, all of these correctness loss functions are defined using basic differentiable computation operations. Therefore, they can be plugged into the existing training frameworks like PyTorch in a pretty straightforward way, where when the auto differentiation technique is also provided. So far, we have identified a termination criterion that ensures correct by construction training pipeline. But there is still one caveat, which is the impact on accuracy. After all, who would like a model that is absolutely safe just because it is outputting a completely naive but totally safe choice? So we want this correct by construction training procedure to have as little impact on accuracy as possible. To do that, a coarse universal abstraction might work for certain local properties, but it may not generalize to broader properties as seen in the example here. So recall that 11.875 was the computed correctness loss for the illustrative example. However, if we simply do a bisection along all input dimensions, the average of this correctness loss in the resulting pieces would reduce by 23%, and while the maximum of the correctness loss in the resulting pieces will reduce by even 48%. If we do that, split the input abstractions into 10 pieces along every input dimension, which is 100 pieces afterwards, then the average of the correctness loss will decrease by 42%, while the maximum of the correctness loss in the resulting pieces will decrease by 83%. In other words, the original correctness loss of 11.875 does not pertain to any real input. It is some fake data that is definitely suboptimal for training. Such unnecessarily large loss is from spurious points inevitably introduced by overapproximation. It is inevitable because the neural network certification techniques did require this kind of sound over approximation to make the entire procedure efficient, especially when handling the nonlinear neural network activation functions. To mitigate this issue, we propose to add yet another edge to the ART framework of correct by construction training, which is to refine the input abstractions based on the exact same loss with respect to the safety constraint phi out. Our notion of refinement here targets at the input abstraction. Basically, it splits the input into smaller regions. See the right diagram, for example. All these three smaller region safety properties, as long as they are proven to be safe, then their composition is also automatically proven to be safe. Because on the right-hand side, the safety constraint, all of them are the same phi out. In this way, it not only introduces fewer spurious data points, but also aligns with the data-driven training procedure more, as right now there can be more training data comparing to a few counterexamples, as we have discussed before. Then we can look at this set of smaller input abstractions during training. Following the correctness preservation theorem, as long as all refined input-output safety properties are safe at the same time the original safety property is safe by construction. For sure, splitting on every input dimension would not be scalable. So we need to refine the input dimensions in a smarter way. Basically, that means to choose only a small portion of dimensions to refine, but not all of them. To do that, recall that our correctness loss function is intentionally defined using differentiable operations. That actually gives us accessible gradients information in extra. Our refinement dimension choice is exactly based on this gradient information from the exact same correctness loss used in the joint training pipeline as shown before. The intuition is that with larger gradients, it usually indicates larger drop of the correctness loss. Specifically, we approximate the average gradients along every input dimension, and then we just pick the largest one to refine. Now we have introduced our ART architecture of correct by construction training framework. It has been evaluated in 2 benchmarks. The first one is the ACAS XU benchmark, where there are 10 safety properties of various domains, and there are 45 networks provided in the dataset. Each one of them has 6 hidden layers, and each hidden layer has 50 hidden neurons. Out of these 45 networks, 36 of them have at least one safety property that is being violated. For these, ART successfully enforces all of them to be safe by construction. In the meantime, the accuracy accuracy impact is mild. Observe that the average accuracy with respect to the original network is more than 96%. Also, notice that the refinement is important here. Without refinement, it fails to generate safe by construction networks in all cases, and also would have about a 2% accuracy drop. The other benchmark we used for evaluation is the collision detection benchmark, where there are a total of 500 correctness properties being used in the dataset, which identify the safety margins around particular data points. There is an original network provided in the dataset which satisfies 328 of those correctness properties, while ART is able to enforce 481 of them with refinement turned on. In the meantime, the accuracy impact is mild. After about 10 minutes of training, the accuracy is 96% and 80.83%. To summarize, in this work, we have proposed a novel methodology to enforce a neural network to satisfy certain safety property phi in a correct by construction way. We have defined the notion of correctness that is a sufficient condition for correct by construction training and can be used in joint training with accuracy aspect losses. Moreover, with abstraction refinement techniques enabled, ART imposes mild impact on the accuracies. Thank you.